This is a foundation survey on reinforcement learning. The following slides shall introduce what reinforcement learning is, where they are applied, and a slight introduction to how they are applied. Reinforcement learning is a type of machine learning. It determines ideal behaviors within a specific context. Furthermore, it allows the machine or software agent to learn from its behavior based on feedback. Reinforcement learning sits in the intersection of many different fields of science. Here, at the middle of the Venn diagram, we have reinforcement learning. And what this illustrates is that for many of these different fields of endeavor, there is a branch of that field that is trying to talk of the same problem that we are concerned about, and that is reinforcement learning. Reinforcement learning, or RL, is essentially the science of decision making. That's what makes it so general and so interesting across many different fields. So this comes again and again. In computer science, we study it under the umbrella of machine learning. In engineering, it comes under optimal control. That is how to optimally decide on a sequence of actions to get the best results at the end of the day, and so on. Why do we need reinforcement learning? To learn from the environment, automated learning. It is used in places where explicit commands fail to work. The current uses of reinforcement learning can be listed as below. To play Atari games, to beat world champions at Go, for robots to stack Legos, simulating quadruped robots to jump over terrains. I'll play the video which showcases Google's DeepMind to play Atari Breakout. So you see, after a few minutes of training, the agent plays the Atari Breakout game much accurately. It scores more points, and by now it has an idea of the moves and controls it needs to do to keep the reward positive over simultaneous and sequential steps. Reinforcement learning. The first concept of RL is that a lot of it takes place as a conversation between an agent and an environment. The conversation basically talks about what is going back and forth between the agent and the environment. The environment is going to reveal itself to the agent in the form of states S. The agent then gets to have some influence on the environment by taking an action A. It also receives back, before the next state, some kind of a reward for the most recent state action combination R. It is the same kind of elements in MDP, but the important thing is the MDP is a kind of a graph structure, and then we get to compute on it. The computations are only in the head of the agent in this case, and the information about the environment is only available through the course of the interaction. Reinforcement learning deals with the learning and sequential decision-making problems where there is a limited feedback. A simple reward feedback is required for the agent to learn its behavior. It is fostered by a positive reinforcement when it does something right and a negative reinforcement when it does something wrong. Characteristics of RL. So RL is different from supervised learning. There is no supervisor. No one tells us the right decision to take. Instead, it's a trial and error paradigm. We just have a reward or point earned signal. Each action of the agent would fetch it points, like +2, +10, or even -10. There is no supervisor telling which is the best action to take, but an information conveyed if the step taken was good or bad. The reward may not be instantaneous, it may be delayed on even after a sequence of steps. The agent may take the decision now, and many decisions later would it get to know if the decision made was a good one or a bad one. There may be positive rewards for several good steps before a catastrophic negative reward. The steps taken are sequential and the points are added up. Reward. Rewards are positive or negative feedback signals. It indicates what the agent is doing in that time step. Results may also be delayed. The agent's job is to maximize rewards over the course of its actions. For an example, in the Atari game, we can state that there is a positive reward for shooting each block and a negative reward if the ball isn't caught by the paddle. For the quadruped robot example, we can state that it is a positive reward if the robot can successfully jump over the terrain, and it is a negative reward if the robot fails. As stated, we have the problem of sequential decision making. Our goal is to select actions to maximize total reward or future reward. Actions may have long-term consequences, and it may be better to sacrifice immediate reward to gain more long-term reward, which kind of brings us to a very specific topic here, which is exploit or explore. Exploit is when the agent exploits known information to maximize the reward, and in explore it finds more information about the environment, letting go of what currently it has in hand. History and state. The history is a sequence of observations and actions and rewards. It is a combination of what the agent sees and gets rewarded for the action it has taken. And it is all observable up to the time t. So what does it do next? The agent selects actions, the environment selects observations and rewards for the action taken by the agent. The state of an agent is the information used to determine what happens next. The state is a function of history. An information state contains useful information from history, so it's also known as history state. A state ST is a Markov state if and only if the probability that the next step given the current step is equals to the probability of the next steps given the history of all the steps that the robot has taken till the current step. It means that the future is independent of the past given the present. Once the state is known, the history may be thrown away. The state is sufficient statistic of the nature. The environment state is Markov, the history is Markov. This brings us to environment states. The environment state is the environment's private representation. It denotes the data which the environment chooses to pick for the next observation or reward. Environment state is not visible to the agent. Even if the environment state is visible, it may contain irrelevant information. Agent state. The agent state is the agent's private representation. It denotes the data which the agent uses to pick for the next action. It is the information used by the reinforcement learning algorithms. It can be a function of the history of the previous states and actions and observations. For fully observable environments, we have the agent state equal to the environment state equals to the information state, and it can be modeled as a Markov decision process. Partially observable environments, an example of which can be stated as a robot not being told its location when it is in a given environment An oil or mining company trying to build a new oil rig or a mine where it has a partial idea or half an information of the exact amount of resources down there, a trading agent not knowing the current prices of stocks before investing in it. Here we can see that the agent state is not equal to the environment state. It is usually modeled as a partially observable Markov decision process or POM-DP. Here, either the agents must have a complete history of the actions they have taken, which is space consuming, or they must have a belief of the environment state using a probability distribution function, or they should use a recurrent neural network, which also signifies here as reinforcement learning. Now, what is a policy? A policy defines the agent's way of behaving at a given time. It is mapping from perceived states of the environment to actions to be taken when in those states. It corresponds to what in psychology would be called a set of stimuli-response rules or associations. In some cases, the policy may be a simple function or lookup table, whereas in others it may involve extensive computation such as a search process. The policy is the core of a reinforcement learning agent in the sense that it is alone sufficient to determine the behavior. In general, policies may be stochastic. Value function. Value function specifies what is good in the long run. Value of a state is the total amount of reward an agent can expect to accumulate over the future. Rewards are given directly by the environment, but the values must be estimated and re-estimated from the sequence of observations an agent makes over its entire lifetime. The most important component of all reinforcement learning algorithms is a method for effectively or efficiently calculating values of the value function. Formally, we typically write the value function as this. The value function depends on the way the agent is behaving, so we index it by pi. If we have a robot which is falling over a lot, that robot would get a very different total reward than the robot that is standing up. So the rewards for every step is accumulated, and the reward we get depends on the policy. Value function for a policy tells us how much reward we are going to expect at time step t. We add up the reward for the time t and then the next step and then the next step. It may also have a discounting or diminishing returns depending on the value of gamma. Model of the environment. We have seen the policy or value function. Now let's talk about models. Model is basically not the environment itself, but sometimes it is useful to imagine what the environment might do, to learn the behavior of the environment and use that model of the environment to help make a plan. So specifically, we have two parts to one model: transition model and reward model. Transition model is basically predicting what the next step would be given the dynamics of the environment. We can also predict how much reward we would get, like reward for not crashing, and so on. So let's try to make it into a very simple example, which is a maze. The idea is to start here and end here. We want to finish it as quickly as possible, so we have a -1 reward for every time step. Optimal control would be to move in the least number of steps possible. We have 4 ways to traverse, or 4 actions, and the state is the agent's location. Policy. An example of a policy would be these arrows. What the agent would choose to do if he were at any of these following steps. Value function. The value function looks something like this. This is the value function for each step. So if we are just one step before the goal, the value function is -1. 2 steps before the goal, the value function is -2. As we trace back, we would find at the start the value function is -16. If you are taking a wrong turn somewhere, the value function decreases even further, as you would find that here in the opposite place where the robot is not supposed to be, it even increases to -22 and so on. Now that we have these values, it is easy to create the optimal policy. And finally, we have a model. Let's say agent has seen a trajectory and moved around like this path as shown in the diagram and has reached its goal. So it's trying to build a map of the environment. It is trying to figure out what will happen in the environment. The -1 represent the reward per step. The map represents what is it to move around step to step. So now we can categorize the RL problems. It is categorized by which one of the key components the agent contains. Let's say we have an RL which is value-based algorithm. If it has a value-based function, then the policy is kind of implicit. Just it has to read out the values and pick out the best action. The next is policy-based. Here we have a policy instead of a value function. So we have a policy without explicitly storing the values. The next is actor critic. Here we use both a policy function and a value function. It's kind of using the best of both worlds. There are two types of sequential decision problems: reinforcement learning problem and planning problem. I'll explain these two with the Atari example. Atari example. This is an example of reinforcement learning. Here, we are not told how the emulator works, we just figure out it's working through trial and error. We do not know the rules of the game either. We just see the score on the screen and get to control the joystick. Depending on the rewards and observations, we create a value function. The value function gives the agent an estimate of the reward it is about to receive. We update the value function every iteration of the game. Atari example planning problem. So what if somebody told us how the emulator works? What if we actually had access to a perfect emulator? We are able to do a look ahead with the emulator, and the rules of the game are known. We can also query the emulator and get to know the exact outcome of our control statements and actions. So if I move the joystick right, we end up on the right, and we move the joystick left, we end up on the left. Here we have a tree search. We can look ahead, search, and plan our next steps. We can plan steps ahead and have an estimate that if we make such steps, we can get a certain amount of positive reward, and we can plan accordingly. So to conclude, reinforcement learning uses a trial and error paradigm to get to know what's best for the agent. The agent gets a probabilistic estimate of the state of the environment with time. Each action the agent takes in the environment, it changes its sequence of action and would be rewarded positive or negative for the same. It tries to maximize points collected over the entire course of action in the environment. Questions?